Hi guys, this is Sakshi and I welcome you all to my direct platform, Way to Learn. So, we are going to solve some of the PYQs from thermodynamics and it would be like we have already finished some of the PYQs from thermodynamics. So these PYQs will be from June 13 to December 13. So all those PYQs will belong to the subject thermodynamics because I have already like made videos on some of the topics of thermodynamics. So if you solve these PYQs, it will be helpful for you to understand better. So let us see our PYQs. So I hope we have already according to me we have already solved around 10 PYQs. So we will be solving the question number 11, which is from CSIR-June 2013. And here 10 grams of ice at 0 degrees Celsius is added to a beaker containing 30 grams of water at 25 degrees Celsius. So just imagine the situation that ice is added to a beaker of water. um, what is the final temperature of the system when it comes to thermal equilibrium? So you have two uh, materials, like one is the ice and another is the water. So now you'll have to find, when you mix them both, you'll have to find the final temperature of the system when it comes to thermal equilibrium. Okay, so basic thing that okay, it is also given in the question the specific heat and the latent heat. So now you'll have to think that how can I approach this question, because it's already given in the question. You have been given the hint, which is like specific heat of water, latent heat of melting of ice. So now you have these uh, parameters given. Now you can think, okay, now I have to solve from using these parameters. I have to think what kind of formula I can use in order to find the answer for this question. So remember, when you have such kind of question, when ice is melted into water and then water to steam, all such kind of questions are belonging to latent heat and the specific heat. Okay, so we will just find here the heat required to melt ice. Like you're going to find the heat required to melt ice. Okay, and then you'll also find the heat required, uh, like amount of heat present in the water. Okay, so when you when you find the heat required, and when you find when the heat required is greater than heat present. Okay, then what can you do? And when the heat required is lesser than the heat present, then what will be the answer? So, basic thing for these kind of question is that you will have to find the heat required. Okay, heat required and heat present. Okay, so now the heat required to melt ice will be Q is equal to ml. Okay, because we have given the latent heat of melting of ice. So according to that, you get Q is equal to 800 cal, and then the amount of heat available in water uh, can be found using Q is equal to mCV into T. CV here is the specific heat capacity, which is given already in the question. So now you have related the given with the formulas, and now you are going to find the heat. If you see here, the heat available is only 750, and whereas the heat required is 800. So obviously the ice will not melt. So whenever the heat available is lesser than heat required for any kind of question, then your final temperature at equilibrium will be 0 degrees Celsius. Always. So whenever the heat available is lesser than heat required for any such type of question, the final temperature of the system at thermal equilibrium will be 0 degrees Celsius. So this is an important thing that you'll have to note. Okay, so this thing is important. So if you just remember that heat, when heat available is less than heat required, then TF will be 0 degrees Celsius. Okay, so let us see the next question, which is from again June 2013, and this is from calorimetry principle. Here, just remember what kind of question have been already asked, and they can again ask the similar type of question. Just they'll be like here you had ice and water. You may get a question with steam and like water and steam, water to steam. Okay, so you just have to relate the given in the question, and then you'll have to find the solution, find a think about a formula, and then substitute. You'll get the answer. So now let us see this question. A vessel has compartment of volume V1 and V2 containing an ideal gas at pressure P1 and P2, temperatures T1 and T2 respectively. If the wall separating the compartment is removed, the resulting equilibrium temperature will be. So this, if you get any question like this, like you have two compartments, and then each compartment has a volume V1, pressure, temperature, and then when you're mixing the two compartments together, find the equilibrium temperature. Okay, whenever you get such kind of question, equilibrium temperature, two compartments, calorimetry principle is the only answer. So let us use that. So here these are the two compartments, 1 and 2, with V1 P1 T1, V2 P2 T2. So using calorimetry principle, the only thing, okay, if you see in the question, is given that is an ideal gas. Okay, so for an ideal gas, C1 will be equal to C2. Hence, using calorimetry principle, you can find this formula. I have already provided the formula, so you can check my thermodynamic videos if you haven't already done. So please check that. You're going to get this formula for equilibrium temperature. So now we also know that PV is equal to nRT, right? So for compartment 1, it will be P1 V1 is equal to N1 RT1, and P2 V2 will be equal to N2 RT2. So using this, we can find N1 and N2. You just have to substitute for N1 and N2 in this formula. So when you do that, you're going to get this. So simple. This is your equilibrium temperature. Only thing you have to remember is, if you get such kind of question of compartment equilibrium temperature, you're going to use calorimetry principle, and you're going to like remember those formulas. If you haven't remember yet, please take your formula notebook, read it, write it 3 times. You're going to remember this. Okay. So let us see the next question, which is from CSI December 2013. And here, a very simple question. Okay, consider the melting transition of ice into water at constant pressure. Which of the following thermodynamic quantities does not exhibit a discontinuous change across the phase transition? A very easy question, phase transition question. So I have already told in my first PYQ videos, I have explained about the phase transition, like what are the quantities that are continuous and what are the quantities that are discontinuous. Please see that and then do this question. This is very simple. I don't have to explain this, but I'll just tell you. Ice to water is the first order phase transition. You'll have to remember this, ice to water, and I have also given the examples uh, for first order phase transition, second order phase transition. Okay, and also the quantities that are continuous and that are discontinuous. Okay, so in here, first order transition, Gibbs free energy will be continuous. Okay, so yeah, so Gibbs free energy will be continuous. Therefore, this will be the answer. Okay, next is a simple problem. Just you have to think. Okay, two different thermodynamic systems are described by the following equation of the state. This one is the first state equation, and T2 is the second state equation. And then T1, comma 2 and Tn and U are the same. The temperature, mole numbers, and the internal energies of the system. Nr is a gas constant here, so you do not have R1, R2, and R. So let U T total denote. T TOT is U total, denote the total energy when these systems are put in contact and attain thermal equilibrium. The ratio U1 by U total is what? So just think that you have two compartments, not two compartments, just two things, like two boxes, and you're mixing the energies within the boxes. So basically the U total will be U1 plus U2. So that will be the U total. So I'm just using that concept, U1 plus U2. Energy will just add up. Then you have U1 and you have U2. Just substitute that. You're going to get U total. And then remember, what is the question over here? At thermal equilibrium. They are asking at thermal equilibrium. At thermal equilibrium, which means the temperature in the first box will be equal to the temperature in the second box, right? So I'm going to use the given in the question. Okay. So on doing that, I get U total as this form. Now I have to find the ratio of U1 by U total, which is 3 by 2 R N1 T1 by R T by 2 3N1 plus 5N2. You can just do this by yourself. Don't check this also. Just pause it and write on yourself. Okay. Uh, so U1 by U total will be this, which will be option B. So this simple thing, just think, uh, you might feel that, okay, it is very simple. Am I right or wrong? Sometimes we just think that, okay, everything will be tough in the exam. No, everything will be easy. It's just a mindset. So if you're sure that, okay, it's just normal energy, when you mix them, energies will get combined. So U total will be U1 plus U2. Just use that and do it. So let us see the 15th question, which is from December 2013. The entropy S of a thermodynamic system as a function of energy A is given by the following graph. So this is the graph, entropy versus energy. The temperature of the phases A, B, C denote TA, TB, TC. So A is one phase, B is one phase, and C is another phase, and their temperatures are TA, TB, and TC. So we have to find which of the inequalities satisfy this particular graph. It's very simple. You just have to find the relation between the entropy and energy and use this graph. Just see the graph, find the relation between S and E, then you're going to get your answer. Okay, so now we know that D is equal to TDS, like du is equal to TDS, which is also the internal energy. So instead of U, I'm going to use E. So dE is equal to TDS. So T will be dE by ds. Okay. Now here I am considering 1 by T is equal to ds by dE. Why? Because ds by dE represents the slope in this graph. Okay. Using the slope, I can explain it to you like, okay, ds by dE is inversely proportional to the temperature. So hence, I can relate the temperature and find the inequality. Okay. So if you see at phase B, there is no slope. It's just a straight line, a constant phase. Therefore, the slope will be 0, and hence TB will be 1 by TB will be 0, then TB will be infinity. Okay, so TB is greater. That is the first thing is TB greater. Okay, next at phase C and phase A, you can see that at phase C the energy will be higher when you compare it with the phase A. This is simple. You can directly say that when at phase C, E is higher than A, therefore E will be greater for phase C and E will be lesser when compared to phase C for phase A, right? So therefore, T here D is like T is directly proportional to T, right? Therefore, you can say that TC will be greater than TA. Else, you can use the slope also and then find the temperatures. So therefore, TC will be greater than TA. Okay, so this is a simple thing. You have to find the relation between the energy and the temperature, and then you are going to use the graph given in the question and then get the answer. Just you have to think, be calm, think what is given in the question, think what you know about, like what kind of formula you can use for this particular question. That's all. So let us see the last question, which is from December 2013, the 16th question. A Carnot cycle operates as a heat engine. So remember, Carnot cycle is also called as a reversible engine. Okay. So operates as a heat engine between two bodies of equal heat capacity until their temperatures become equal. If the initial temperatures of the bodies are T1 and T2, and T1 is greater than T2 here, then the common final temperature is. So we have to find the final temperature. Some sort of tricky question, but we'll just start. Okay, how can we do? Okay, So just read again. I'm just going to read the question again. See, you're having a Carnot cycle which operates as a heat engine between two bodies of equal heat capacity. So heat capacity is equal here until their temperatures become equal. So if the initial temperature of the body, so T1 and T2 are the initial temperatures of the two bodies. Okay. So you are going to find the common final temperature. So the final temperature will be same for the two bodies. It is already given in the question. You just have to find the common final temperature. So, and it is also given that CV for specific heat capacity is same. Okay, so now you know that, okay, we have to find, there is something related to specific heat capacity, so you'll find the specific heat capacity, and then you'll try to use the T1 and T final. For one body, you'll have T1 as initial temperature, and TF will be your final temperature, and for other body, you'll have T2 as the initial temperature, and TF will be final temperature. So the one thing you have to do is find TF, which should be common. Okay, so now we know that it is a reversible process, the Carnot engine. So you know these three things. So you are going to start with that. For reversible process, the entropy will be 0, del S is equal to 0. If you don't know this, write down in your formula notebook, revise it. Okay, so next we know the specific heat capacity, which is Cv is equal to dou U by dou T. Since Cv is same for both uh, the Cv is same, I can consider that du is proportional to dt. Okay, so also du is equal to tds. Now I know that du is proportional to dt. I can write, instead of du I can write dt, which is equal to tds. So ts will be equal to dt by t. So this is the relation for entropy which I have found. Ts is equal to dt by t. Okay, so now ts1 will be equal to t1 to tf. Now I'm just going to integrate, so I get the entropy for first body and the entropy for the second body. Now on integrating I get log Tf by T1, and similarly for the second body I get log Tf by T2. Now we know that del S equal to 0. Okay, so now we'll have to use del S. Usually del S means like we just find the difference, but here it is the change. Okay, now you can also see that I have just added S1 plus S2, but if you like, if you try and minus it, S1 minus S2, then you're not going to get the answer. You can try that first. So once you try S1 minus S2, you're not going to get any kind of option over there. Then you can come for S1 plus S2 equal to 0 over here. Okay. Now you're going to do that, and then on substituting and using some rules of mathematics, we are going to get Tf square is equal to T1 by T2. You can also see that here I have used log Tf square by T1 by T2. So on taking exponents, like exponent on both sides, you're going to get e power log Tf square by T1 T2. E and log will get cancelled each other, and your RHS will have e power 0. So Tf square will be equal to T1 by T1 T2, and Tf will be equal to root over T1 T2. So this was the last question of this video. Thank you. Like my videos, share my videos, subscribe my channel, and do not forget to hit the bell. I'll try to upload more videos for the upcoming exam, and also for the GATE exam. I have already started like PYQs. I've finished 10 PYQs of GATE. So I'll be uploading those two, and the next subject I'm going to show you, like post videos on the next subject, will be quantum mechanics. So those who love quantum mechanics, or those who like just stay away from quantum mechanics, you'll find it easy, and the problems to solve will be very easy, and you'll be interested in solving the problems of quantum mechanics. So stay tuned for more videos. Thank you. See you tomorrow. Ta-da.